Alright, welcome back to the second half of this lecture about phase transitions of water. Now we've already talked in fairly painful detail about the whole story of what happens when ice melts or liquid water freezes. Let's talk about some other transitions. How about evaporation and condensation? Evaporation is when water that is a liquid changes into water vapor, a gas. And here's a guy stepping out of the shower here. He's currently covered with liquid water, little drops of liquid water all over his skin. And he's going to step out into the room and start drying off. As he steps out, water is going to start evaporating off his skin. How is he going to feel? Well, you already know. He's going to start being cold, right? When the water starts evaporating off your skin, you feel cold. In fact, water evaporating always makes you feel cold, come to think of it. I mean, that's what sweating is for, right? We perspire when liquid water comes out of your sweat pores and evaporates off the surface of your skin. Clearly, in the framework of this business of latent heat and specific heat and cooling processes and warming processes and all that stuff, clearly evaporation is going to have to fit in this business of a cooling process. But how are we going to get there? Well, once again, let's actually watch one of these videos. You can use the PowerPoint to get to those links that I had there, and you can actually watch them yourself and read the text that I have on there, or you can use the screen capture of it I have right here. But let's talk about what actually happens when water evaporates. When water evaporates, liquid water molecules that are sitting at the surface on your skin are moving around, but they're not moving around all that much. At some point, they're going to leave the liquid water on your skin, they're going to evaporate, and become part of the air around you in the form of a water vapor gas. But those gas molecules that are zipping around in the atmosphere, they're moving fast. I mean, at typical temperatures and room temperature, molecules are moving at about 1,000 miles per hour. So for that molecule who's currently hanging out as just a little drop of perspiration on your skin, he's going to have to gain a whole lot of energy from like being bumped by air molecules and oxygen molecules and nitrogen molecules, or being bumped by the molecules that make up your skin and so on, your body, to give it enough of a push that it now has enough energy to go and leave and become a water vapor molecule. It's going to have to absorb a lot of heat from the environment around it. It's going to have to be a cooling process, which makes sense. The liquid water cooled as part of it evaporated away, or it took heat from its surroundings and carried that heat away. Once again, we have stored sensible heat that we could have been measuring, like when the guy stepped out of the shower, his body was some temperature. That was sensible. We could measure it. It could be sensed. But we've hidden it. It isn't like those water vapor molecules up there in the atmosphere are hot, but heat is being hidden. It's hidden in the fact it's not liquid water anymore. It's water vapor. It's latent heat. The heat is hidden. It's latent. And as we've said, clearly evaporation is a cooling process. And it is a big cooling process. It cools, it absorbs heat from its environment at a rate of 600 calories per gram. 600 calories. In other words, 1 gram of water vapor, 1 gram of liquid water at, let's say, 20 degrees Celsius. If you add a whopping 600 calories to that water vapor, you can convert it into 1 gram of water vapor at the same temperature. You haven't actually made it any warmer, you've just given it enough energy that it's no longer just kind of moving around slowly in the form of liquid water. Those molecules are crouching around all over the place. Oh, 600 calories per gram. No wonder you get cold when you step out of the shower. As you step out of the shower, only a tiny bit of water evaporates in those first few seconds. But it's enough that you're cold and you're like, where's my towel? Where's my towel? Because you're cold, right? Because even a tiny bit of water that evaporates absorbs a whopping amount of heat. Oh, and the opposite of evaporation is condensation. Condensation is changing water vapor back into liquid water. If evaporation was a cooling process that absorbs heat from the environment, if condensation is going to be the opposite, apparently condensation is a warming process that releases heat into the environment. In fact, that's exactly right. Changing water vapor molecules, which are zipping around at 1,000 miles per hour in the room, and getting them to stick together and condense and form like a droplet of water or a droplet of rain or whatever, involves them losing a lot of heat. in fact, works out to, unsurprisingly, the opposite. It's 600 calories per gram. Making 1 gram of liquid water involves releasing 600 calories of heat that used to be latent, now into sensible heat into the environment around it and warming the environment up. So, for example, if you have 1 gram of water vapor in the form of, gas in the room at like 20 degrees Celsius, and you could convert that into 1 gram of liquid water at the same temperature, and you'd get 600 calories of heat to release into the environment to do things like warm up the air or whatever. This is hugely important in meteorology. Let's think about the formation of a cloud. A cloud is where we have taken water vapor in the atmosphere and we have condensed it into little liquid water droplets. Every gram of liquid water that we condense in that manner releases a whopping 600 calories of heat into the environment. And there's a hell of a lot of grams of water in a cloud. A typical puffy, happy little cloud passing by on a summer day has more liquid water in it than an Olympic-sized swimming pool. There's a lot of grams of water vapor up there in that thing. And every one of those grams released 600 calories of heat into the air around it. Latent heat release by condensation in a cloud is a warming process. It's going to make the air around it warmer. And that's going to be hugely important to the processes that make thunderstorms and other kind of cloud structures and why hurricanes were where they do, and we are going to be coming back to that time and time again. Condensation releases latent heat. It is a warming process. All right. So we've built a second piece of this chart. Again, I'm covering up the parts we aren't talking about right now. But remember, now we have the part that's about liquid water and gas. And how, like with the red arrow here, we have evaporation, where we are absorbing heat from the surroundings around it at a rate of about 600 calories per gram as we change the liquid water into water vapor. Or like with the blue arrow there, we have condensation, where we change water vapor into liquid water droplets. That releases heat. It releases a whopping 600 calories per gram. Wow, that's a huge amount of heat. In fact, that's got all kinds of important meteorological phenomena, but just because your book mentions it right here, I will too. That's part of the story about how we make forecasts of how cold it'll get overnight when we make forecasts. Overnight, the temperatures of the air are going to get colder and colder. Probably not hugely surprising to you. I mean, the sun's not up, we're not providing shortwave radiation. Oh, I don't want to bring back nightmares from Module 1, but you're probably not terribly surprised that it gets colder and colder at night. Until we start to form dew. Dew is little liquid water droplets that form on grassy surfaces and tree leaves and windows and stuff like that, where water vapor starts to condense into little droplets. And every gram of that liquid water that forms on the grass, on leaves, on your windows, whatever, releases 600 calories of heat into the air, which is a lot of heat. So at night, it's getting colder and colder and colder, but at some point, and we'll get to later in this module actually why, at some point we're going to start forming dew, and when we start forming dew, that will release latent heat by condensation into the environment, and it won't get colder anymore. So most nights it gets colder and colder and colder, and then at some point it stops getting colder until morning, because we're forming dew. There are not vast amounts of dew out there in your yard. It's not like there's gallons and gallons of water when you wake up in the morning out there on the grass, but every gram, which is barely anything of it, released 600 calories of heat to the air. Of course it didn't get any colder after that. It's pretty cool how that works. We've already talked about freezing and melting, which move back and forth between solid and liquid. We've already talked about evaporation and condensation, which moves back and forth between liquid and gas. Now, we're not as familiar with it in our day-to-day lives, but there are also the big steps, sublimation and deposition, where we go back and forth between solid ice and water vapor without ever being a liquid in between. So for example, deposition is changing water vapor directly into ice without it ever having being a liquid in between. The classic example of this in your day-to-day life is frost. Frost is not frozen dew. When you get up in the morning on a winter day and there's those lacy patterns of frost on your windows or on your car windshield or on tree branches or whatever, that frost formed by deposition. Water vapor went directly to the ice phase without passing through liquid on the way. There are other examples that happen inside of a cloud and so on, where deposition, will change water vapor into ice crystals in clouds and so on, which we'll be seeing even later in this module. But for now, frost is sort of your canonical example of that. All right. now that we're kind of seeing the pattern of this, it's probably not terribly surprising to you that the deposition of ice will be a process that releases heat, right? Those water vapor molecules that are moving around real fast are going to give up tons of heat to form an ice crystal. They got to stop moving around. They're going to give off heat to the environment. It's a warming process. Every gram of frost that you form by deposition is going to be releasing a whopping 680 calories per gram. That number probably is not a huge surprise, right? It took 80 calories to get to a liquid, and then another 600 calories to get to being a liquid, and then another 80 calories to go from a liquid to being a solid. Probably not a surprise that it's 680 calories per gram. So in other words, if you have 1 gram of water vapor at a temperature of 0 degrees Celsius, you can convert it to 1 gram of ice, frost, and you're going to get 680 calories to release into the air around you. Wow. Deposition releases an enormous amount of heat. The opposite of deposition is sublimation. And sublimation is when you change ice directly into water vapor without it ever being a liquid. In your day-to-day life, the best example of this is a frost-free refrigerator. Older refrigerators tended to not be frost-free, and water vapor that got into the freezer tended to form big blocks of ice in the back of the fridge, and periodically you had to clean that out. Newer refrigerators are generally frost-free. Sensors inside of the refrigerator monitor the temperature, pressure, and humidity in such a way to sublimate any ice that forms. Ice converts from solid back into water vapor in the freezer, and then the next time you open the door, you see that kind of cloud sort of thing, and the water vapor is coming back out. Okay, that's sublimation. Okay, sublimation is changing ice into water vapor. Another example of sublimation is how I clean my car windshield in the winter. When I had to park outside because my garage is a disaster, and when I park outside, of course, in the winter I get frost on my car, and I probably should be a responsible person and scrape it all really good, but do I? Hell no. I scrape a little, I'm a tank driver. I scrape a little area in front of my face and I hope for the best. And I drive a mile down the road, and by the time I get that far, the windows are clear. That's because the ice sublimated. It changed back into water vapor. It didn't melt and run off. It didn't melt and then evaporate. It changed it right from being a vapor into being, from being ice into being a vapor. Ice cubes in your fridge, if they wait too long in the freezer, they kind of get smaller with time. That's sublimation as well, and so on. Some people would say dry ice is sublimation. You guys know what dry ice is. It's frozen carbon dioxide. You can use it at Halloween to make certain kinds of special effects and so on. Some people would say it's dry ice as an example of sublimation. That's kind of a question of how you define it. If you look up in a dictionary, sublimation usually specifically has to be water substance. Carbon dioxide is not made of water, so it doesn't count as sublimation. But I think like your textbook said, that's sublimation too, right? Dry ice doesn't melt. Dry ice is frozen carbon dioxide that turns into carbon dioxide gas. If that isn't sublimation, it's pretty damn close, okay? So, sublimation is a warming process as we release all of this heat back. Sublimation is a cooling process as we absorb heat from the environment. Alright, so we built another layer of this diagram. In fact, it works really well if we take a look at the whole thing. And again, you have this diagram drawn slightly differently in your textbook, a zillion different websites, you have it here, and so on. And what I want you to notice is that there's a pattern to it. Once you've actually drawn it this way, you'll see that some of the processes are going from left to right on your diagram, and some of the processes are going from right to left on the diagram, as you have it written from solid to liquid to gas. And what I want you to notice, because this will help you remember it, is there's a pattern to it. The ones that are going from left to right on the diagram are all cooling processes. They're processes where heat from the environment and the surroundings is being absorbed and hidden. It's still there, but it's hidden. It's hidden in the fact that these molecules are moving around as they changed phase. And all the processes that go from right to left on this diagram, like the blue arrow on there, are warming processes. They are releasing heat into the environment. I strongly disapprove of the choice of colors that this artist used when they made this slide, but that's another whole story. Alright, once you notice that pattern, though, it becomes much easier to remember which of these transitions is which. Alright. I can't even begin to tell you how important phase transitions turn out to be in meteorology. Just to give you some examples at this time here. In a hurricane, we have very strong winds in a hurricane. We'll learn all about hurricanes in Module 7, I think it is, of the class. They produce these strong winds as they blow across the ocean, produce enormous amounts of evaporation. Evaporation means every 1 gram of water that you evaporate off the surface of the ocean, it takes 600 calories of heat from around it and absorbs it. It absorbs that heat from the ocean. There's a lot of grams of water in a hurricane. So think of the enormous amounts of heat that have been absorbed from the ocean and hidden in the fact it's water vapor in the hurricane. Then the moisture will condense out when we have the rains in the hurricane, and it will release that heat up high in the atmosphere. That's going to be driving the thunderstorms and so on that make the hurricane in the first place. Oh, so phase transitions of water, what happens where we evaporate it and what happens where we condense it, is part of what drives a hurricane. If there's dry air under a rain cloud, the cloud, as the liquid water falls through that layer of dry air, it might evaporate. We're going to learn about that. That process is called virga. We'll see that later in this module. As it evaporates, evaporation is a cooling process. Every gram of water that evaporated as it moved through that dry layer of air absorbed 600 calories of heat around it. And there's a lot of grams of water vapor, liquid water falling here. We're doing an enormous amount of cooling as the liquid water droplets fall through this cloud. That can mean lots of different things, but just as an example, there's certain kinds of storms that happen in Africa where weather systems are driven by that formation of cold air as rain falls through a dry layer. As the rain falls through the dry layer and evaporates, it cools that layer, which creates other weather phenomena that are part of this process of how the supercool water forms and so on. That in and of itself, the example isn't where I'm going here. The point is, we're going to see lots of examples where these phase transitions are important all over the place in meteorology. So just to review, all of these neat things about water and weather are all due to this really unusual nature of water. It's a polar molecule with a very high specific heat. The highest specific heat of any natural material on Earth. We don't have things like liquid hydrogen and solid helium and stuff like that on the surface of the Earth. I think compressed natural gas maybe has a higher, but again, that doesn't occur naturally on Earth, in the compressed state anyway. It occurs naturally on Earth also in 3 phases. Very unusual material in that regard, right? Then we talked about the business of all these phase transitions, melting, freezing, evaporation, condensation, sublimation, deposition, and what they all meant in terms of which ones were releasing heat and which ones were absorbing heat. That's going to have everything to do with the things we're going to see further on in this module when we're talking about things like formation of clouds and formation of rain and so on. And then as we start putting this all together into weather systems like hurricanes and thunderstorms and so on, we're going to be able to fall back on these skills about understanding about moisture and phase transitions of water. All right, that's the end of this lecture. Let's do 3 quick questions before we go. Question 4. Sublimation is considered to be a blank process because it blanked the environment. Hey, didn't we see this question before? Wasn't that question 3? Yes, just like question 3, I cut and pasted, except I changed melting into sublimation. Which of these combinations of warming and cooling and releases heat into and absorbs heat from is right for sublimation? Make a choice from those 4 options and get a little feedback before you move on to question 5.